Hello and welcome to the last part of homework 4. So now we get to derive an expression for the steady state absorption flux of gas A into a liquid film of thickness beyond which the concentration is approximately 0. How exciting. Okay, let's start by drawing this out. So we're going to have a container, and this is going to all be liquid. This is all going to be vapor. And then this part is the film thickness, is delta. And then on the left side here, the concentration of A will be equal to 0. And this is a first order reaction, so it's going to be negative rate. It's going to be equal to the rate constant times the concentration of A. So that's our setup. So we can say that at the vapor-liquid interface, that the position is going to be equal to 0. And then on the other side, the position is going to be equal to the total film thickness. And then to solve this, it says here that the diffusion can be described by Fick's diffusivity. So let's use Fick's law. So we're going to say that the molar flux component A is going to be equal to the negative diffusion coefficient of A through B times the change in concentration of A over the change in position. So the overall balance here is going to be in minus out plus, it's like in minus out plus accumulation, but it's going to be plus the reaction rate. Going to be equal to 0. So if we model this as a box, we're going to have in minus out, this is going to be the concentration, and this is going to be the change in concentration over the change in position. So that's going to be this in minus out, and this is going to be equal to the negative reaction rate, where we said that was up here. Negative reaction rate is equal to KCA. So I'm going to move this, or I'll just copy this down to put everything kind of together. Okay. So then we want to take for this equation, we want to take the derivative of each side and then set it equal here. So if we do that, we're going to end up, oh, sorry, this should be the molar flux. This is an A. There we go. So now, if we take the derivative of each side, we need to set it equal here. So this would be the derivative of the molar flux of A with respect to position is equal to, this part stays the same, but looking at this equation, it'll be negative diffusion coefficient AB, and this is just going to be the second derivative. So then putting all of this together, we're going to get that the second derivative of the change in concentration with respect to position is going to be equal to the negative reaction rate constant over the diffusion times the concentration of A, and then this will all be equal to 0. And now we want to evaluate it at the boundary conditions. Oops. Ca at Z and the concentration of A at delta. Or rather, this will be the concentration at Z is equal to delta, and the concentration of A at 0 is going to be concentration of AI. That's going to be over at this side here. And then let me just rewrite this up here. To be minus and minus. That way we have like one uniform equation. So we want to solve for the concentration of A. So to do that, we're going to have a variable, let's say it's M. We're going to set it equal to the square root of the reaction rate over the diffusion coefficient of AB. Now if we rewrite this, we're going to have the second derivative of the concentration gradient going to be equal to m squared times the concentration. So now we get to solve this differential equation. We get that C is going to be equal to some constant A times the hyperbolic sine of mz plus some constant times the hyperbolic cosine of mz. Right. And then when z is equal to 0, the hyperbolic sine function is going to be equal to 0, and the hyperbolic cosine is going to be equal to 1. So that leaves us with the concentration of A, it's going to be equal to B, whatever that constant is. So this is going to be at the interface. Okay, so now we want to solve it where Z is equal to delta. So that's going to be concentration when Z is equal to delta, we said was 0 up here. So it's going to be 0. It's equal to some constant A times the hyperbolic sine of m delta plus some constant B times the hyperbolic cosine of m delta. And then we already solved for B. We said that B was the concentration of A at the interface. So to solve for A is going to be equal to negative concentration of A at the interface times the hyperbolic cosine of m delta over hyperbolic sine of m delta. Right. So now we want to plug in A and B to our general equation. So we have that the concentration of A is going to be equal to A, which we just found, times the hyperbolic sine of mz plus B, we said was concentration of A at the interface, times the hyperbolic cosine of h mz. So now we can factor out this concentration of A at the interface and give it a common denominator. So we're going to have that concentration of A is equal to concentration of A at the interface times the hyperbolic sine of m delta times the hyperbolic cosine of mz minus the hyperbolic cosine of m delta times the hyperbolic sine of m delta all over the hyperbolic sine of m delta. All right. And now we get to use the angle addition formulas, and this will simplify to the concentration of A be equal to concentration of A at the interface times the hyperbolic sine m delta minus z over the hyperbolic sine of m delta. And then if we remember back to the beginning of the video, we said that the molar flux of component A was equal to the negative diffusion coefficient times the concentration gradient. We are trying to solve for the molar flux of A. Okay, so we can take the derivative here because we have this term. Let me use something different. This term, we need to take the derivative of this whole thing, and then we can plug that derivative into this into the Fick's law equation. So the derivative here, okay, the derivative, this is going to be the concentration gradient with respect to position. It's going to be equal to concentration of A at the interface times, there should be this times m, times the hyperbolic cosine m delta over the hyperbolic sine of m delta, and this will be a negative. And now when we plug this in right there, we get that the molar flux of component A is equal to the diffusion coefficient times m times concentration of A at the interface times the hyperbolic cosine m delta over the hyperbolic sine m delta. And then if we remember that m is equal to the square root of the reaction rate over the diffusion coefficient, we can plug that back in to these m's here and simplify. We get that the molar flux of component A is equal to the square root of reaction rate times the diffusion coefficient times the concentration of A at the interface times the hyperbolic cotangent m delta. But basically this is simple enough with the equation for how to find the molar flux for a steady state absorption with a film thickness beyond the concentration using Fick's law.